Suppose, for example, I now want to define the hyperbolic tangent. See y equals hyperbolic tangent x. How could I do that? Well, I mimic the circular function definition. I say, okay, I will define the hyperbolic tangent to be the hyperbolic sine over the hyperbolic cosine. By the way, in the same way that one can show in terms of geometric constructions on the unit circle how one constructs the tangent and the cotangent and the cosecant and the secant, etc., once sine and cosine are given, it can also be shown that we can construct these things in terms of geometry from the hyperbola, but because that gets computationally involved, I've also saved those aspects for the exercises. In other words, I'm not going to worry about how you construct the hyperbolic tangent given the hyperbolic sine and the hyperbolic cosine right now. All I'm saying is, suppose you've made up this definition and now somebody says, gee, I would like to find the derivative of the hyperbolic tangent of x. What I want to point out is that the recipes that we need are no different from anything that we've had before. Namely, since the hyperbolic tangent of x is sinh x over cos x, I use the same quotient rule as I used before. Namely, to differentiate the hyperbolic tangent, I differentiate this quotient. How do we differentiate a quotient? It's the denominator times the derivative of the numerator. Well, the numerator is sinh x. The derivative of sinh x is cos x. That gives me a cos squared x over here, minus the numerator, which is sinh x, times the derivative of the denominator. Well, the derivative of cos x is sinh x. That gives me another factor, over the square of the denominator. Now, my basic identity is that cos squared minus sinh squared is 1. So this is just 1 over cos squared x. And if I want to write this all on one line, I can invent the notation that the hyperbolic secant is 1 over the hyperbolic cosine. In other words, I can invent notation like this. But again, the important point is not so much what this answer is, but how I can derive it from first principles. And by the way, in terms of the inverse derivative, once I know that the derivative of hyperbolic tangent is the square of the hyperbolic secant, I can immediately add to my list of inverse derivatives. Namely, I just have to write down, see, there's an integral formula that I now have. But again, all I want to emphasize here is how the details take care of themselves in the same way as always once we have our basic definitions.